Hi, my name is Jaz. I use they, them. I'm on the Bluesky team. Bluesky currently is a team of around 21 people in the company in total. When I joined the company, we had around 100,000 users a little under 2 years ago. Today, we have over 33 million users, and things have got a little bit exciting in a pretty short period of time. Cool, so who am I? Well, I am a member of the team, seen here with two of my coworkers kind of photobombing. I like to travel. I have some friends I like to go around and see the world with. I like hardware. I'm a very big hardware nut and a home labber. So I have a rack I keep in my apartment. I run some community services for Bluesky and AppProto out of my own apartment. And this actually translated super well to running bare metal on-prem for work, which is very exciting. I have a really cool sister. She works at NASA for now. Hopefully she will continue to be working at NASA, but things are a little tough right now. And what else am I? Yeah, I lived in the Bay Area for the past 5 years. I actually just moved out of the Bay Area, but SREcon, this year at least, is kind of in my backyard. So I decided it would be a great idea to come and tell you all about what we did at Bluesky. So what happened? This is a graph. You're going to see a lot of these. This first graph shows overall request throughput through our backends. On the left side of this graph, this is around mid-October. You see us doing a daily peak of around 5,000 requests, fully hydrated API requests a second. That our daily peak, because we're a social network, usually lasts around 9 hours. And typically our peak is in US time zone. So from around 8:30 a.m. Pacific time to around 4 p.m. Pacific time is our peak traffic. You can see we had some pretty crazy activity going on. In less than a month, we went from a daily peak of 5,000 requests a second to a daily peak of over 50,000 requests a second. That's a lot of scale in a very short period of time. So what happened? Well, I was at the bar one night, and I was watching the after-action report from a Golden State Warriors game, and I saw a Bluesky post on TV. And I said, that's strange. Why is there a Bluesky post on the TV? Then, a few days later, we saw Bluesky rocket to the front or the top of the free apps in every app store in the US, Canada, the UK, lots of major markets. We were at the top of the app store. And a few weeks after that, our CEO, Jay Graber, was interviewed on CNN Live on primetime news at night. So clearly there was a lot of excitement for Bluesky, mostly at the end of the US election in November. We are a kind of open source and open network that has a microblogging app on it, kind of like Twitter. So some of our dedicated users decided to make a fail whale for us that was more in the realm of Bluesky. Our network is made of distributed nodes called PDSs, and we named them after mushrooms. So we have kind of the mycelial network of servers, and our users kind of have this fun mentality where they like to champion the mushroom that they're on. So we have our own fail whale, which thankfully we didn't really need too much. Also, I am our primary on-call at this time, during this incident. I'm usually the shot caller on infrastructure decisions and on scaling decisions, and so I had to prepare for the worst. I collected a large amount of monster cans from my local Walgreens and was ready to get into the action. So, this is a user growth graph. You might notice it looks pretty crazy. In mid-October, Twitter changed their terms of service. This TOS change made changes to how blocks work, and it also changed their AI policy, saying that they could use images uploaded by artists and by users to train AI. This was pretty wildly unpopular with users, and we saw it on our end as a couple million users moving to our network in the course of a week. Then, at the end of November, we saw not a big spike and a fall-off, but a kind of weird hockey stick shape. If you work in SRE, which I'm sure lots of you are familiar with graphs that, or hopefully are unfamiliar with graphs that look like hockey sticks, because they're very scary. Because from day to day, you see continued user growth, and the rate of growth increases as time goes on, and you have no idea when it's going to stop, and you have no idea what to expect. So mapping this back onto the graph we saw before of overall request throughput, we can see when Twitter changed their TOS, we have this big spike to around 35,000 requests per second daily peak. Then things calm down a bit, and then US Election Day happens, and instead of it spiking and calming down, we have this big kind of hockey stick swell. Now, why is this a problem for us? Well, we run on bare metal. This is some of our fleet that runs in one of our two point of presence data centers. We have a fixed kind of capacity when it comes to things like this. So how do you deal with 10x growth on fixed capacity? Let's get a little bit more into what happened that week. We saw 4 different modes of failure during this hyperscale event. The first mode of failure is, software you control goes wrong. That's really easy to fix because you just ship some better, write better code, ship better software. Hopefully you can roll stuff out quickly enough and you can mitigate the issue. What happens next is software you don't control goes wrong. That's a lot harder. You have to talk to a vendor, you have to go dig into Stack Overflow or wherever you can go find more information about other people seeing a similar issue and try and mitigate it yourself. And that's pretty hard. Then you have hardware that you control fails, like a disk failing or a node going down or a NIC failing. Those are annoying, but at least you can do something about it. Those stink because I have to go down to the data center and go swap out a component or something like that. But at least it's within our power to solve the problem. And then finally, hardware you don't control failing. That's probably my least favorite mode of failure because you just kind of sit back and say, there's nothing you can do. At that point, if you're relying on external hardware and that external hardware has a failure and you don't have any kind of backup system in place, you just kind of have to wait it out, call your vendors, and pray. So these each have their own flavors, their own symptoms, and their own remedies. Let's look a little bit closer at that graph from earlier showing requests per second. We see at our peak here, we're up 10x from mid-October, so 50,000 requests a second. And then you can see at the daily troughs, which are usually when we have a breather, we're doing 25,000 requests a second, which is higher than our daily peaks from pretty much historically. So we're both doing way more traffic than we expect, and it is a 24-hour problem because there is no longer a safe time to do anything. So speaking of failures, here's a really dangerous-looking graph. You can see there's some really odd shapes in there, spikes dipping way down into the 32K requests a second range, down from around 50K. So what happened here? Well, there was some pain, and then it ended after about 8 hours, and then there was a little bit of extra pain in there somewhere. So viewing this from the perspective of our East Coast data center, you can see, hey, there's huge traffic drops on our East Coast data center. It doesn't look like there are many errors that are spiking. It mostly just looks like there's not traffic coming in. So what the heck happened? There was an external hardware failure. We had a fiber cut at one of our facilities. This fiber cut sucked because at the time, we were single-homed in this facility, and so we had no easy way to reconverge our BGP configuration or anything like that and shift traffic to our other ISP. So this was pretty painful. The result was about 50% of our users couldn't talk to us, and we had tons and tons of new users joining every day. At one point, we were adding 1 million users a day for 3 days in a row, and lots of them wanted to use the platform, and new users are very excited and want to like things and follow people and post and say, hey, I'm here, it's awesome, and they couldn't do that. So what did we do? Oh, we have 2 data centers. Let's fail over to the other data center. It's a pretty easy thing to do, right? The whole point of having this redundancy is so you can do a failover. So we did a failover. It didn't go great. The failover happened. We failed over all of our traffic in about 5 minutes. Our database cache got thrashed impossibly, really, really hard. Hot shards are now twice as hot. So any popular data, any hot shards you have in your data center, when you suddenly double the traffic, it usually has a similar shape to the traffic that's already there. And so all of our hot data got twice as hot, and we didn't have the right caching infrastructure in place to deal with that. So now all of our users were in a degraded state, and we kind of made things worse by failing our traffic over. So we revert, and you run everything back. So what do we learn from that? Well, it's best to roll with the punches. Oftentimes during an incident, if you make no decision, it can be worse than making the wrong decision. Decisiveness is very important, and you must weigh the costs of doing nothing versus the cost of trying the thing that you can try. For us, we are a small team. We had tried this failover before at smaller scales. It worked fine. We had never tried it at this scale before, but there's a first time for everything. So we learned the hard way that that probably wasn't the best way to do it. So what else do you do with this external hardware failure? You call your vendors and you say, hey, why is there no fiber? Why is the internet down? They will tell you, oh, we have a team there and they'll be done in 6 hours. And then you'll say, oh, all right, can't really do anything about that. You apologize to your users and you update your status page and you say, hey, we're super sorry, we know you all want to be here, but we can't keep the website online right now because of stuff that's outside of our control. You don't want to normalize the fact that these kinds of errors happen on your product. You don't want your users to get used to things being buggy and flaky and bad. So also prioritize dual homing your BGP configuration. Prioritize getting all of those redundant systems or all those potentially redundant systems to be actually redundant so you don't have an issue like this again. And then in the meantime, pray that your vendors get things resolved as soon as possible. So looking back at here, we had about an 8-hour window where we were in very dubious straits of internet activity in our second data center. But we got on the other side of it, things were okay. Then we ran into some more issues later. So this, I'm talking you through the timeline of an 11-day window in November where we were in a situation room 16 hours a day for 11 straight days. Sleep was maybe 4 hours a night because I would wake up, as soon as I was cognizant enough to wake up, I'd wake up and check graphs and make sure we weren't going to die today. And so everybody, as the week went on, as the 11-day period went on, things got worse and worse and worse because we were performing worse and worse, and there were more miscommunications and more fat fingers and more problems. So on the read path, you can see there's a little byte taken out of this graph around, 7 p.m. Pacific time. This is what that looks like. As you can see in this graph, there's a big red spike in there, which means we're serving some errors. So what exactly happened to get us to serve these errors? Well, there was a database node crash, but we're running a horizontally scalable, fully redundant database. Why would that cause errors? We'd expect to see a little spike there, but what's with this whole 30-minute period of pain after the database crash? The node rejoins the cluster, and once the node rejoins the cluster, everything goes to shit. And we're wondering, what happened here? Why is a node rejoining the cluster causing pain? It took us about 30 minutes until things got back to normal. So we saw this first on November 17th. We saw it again on November 20th, several times in that same day, and we saw it again on November 25th. The whole time we're trying to dig in to figure out what the heck is going on here. We don't have the visibility into how the database works to know why these problems are occurring. So this is, of course, it's an external software failure. We use an open source database, so we're not the ones writing the database code. So what do? We get logs, we get core dumps, we get backtraces, and we try to figure out what the heck is going on. We dig through GitHub issues and see, hey, is anybody else having this issue? This is all done in panic, trying to figure out why our database is not working properly. Consult your vendor if you can. If you're paying them for an enterprise contract, use that contract. Talk to your vendors. Get the support that you want. But if you're not doing that, well, best of luck, pray, and keep digging. So we were in the pray and keep digging mindset during these outages. So what actually happened here? We have the database node crashing, which we recover from very quickly because other nodes in the cluster get gossiped and say, hey, that node is down, don't talk to it. But during this rejoin stage, there was a 700 gigabyte or gigabyte core dump that tried to dump itself into AppPort, which if you've ever tried to dump a very large core into AppPort, doesn't go very well. So that failed. It took about 10 minutes of trying to dump the core into AppPort before it crashed. Then when it crashed, it would restart, and we had overeager disk throttling because we had misconfigured our database. So as it restarted, it has to catch up on tens of millions of writes that it missed while the database was down. And so we have tons of NVMe drives. We should be totally fine, catching up on this data. But the database thought it had a lot fewer IOPS than it really did, and this caused it to throttle itself, which made it time out on all sorts of operations, which instead of that timeout meaning that node has problems, it ended up meaning the whole cluster has problems, and all of the users trying to make queries to that cluster were having problems. So the DB installation was misconfigured. There were noisy neighbor workloads. We had one big database cluster that we were using for pretty much everything at the time. One of those workloads was incredibly write heavy. That's now shifted to its own database cluster, but it was causing these huge walls to have to get caught up on. There was aggressive self-throttling because we had misconfigured things. there was no surface visibility of any of these issues. So during normal operations and in any of our dashboards, we couldn't see why this was happening. There is, if you dig deeply enough in one of the most detailed dashboards that the database has, you can see where it's self-throttling. So eventually that's what we found that led us to the conclusion that, oh, we need to tell it has a lot more IOPS and tell it has a lot more bytes per second of read and write throughput. Cool. Now we can talk a little bit about the write path. So that was the read path, that was read scaling. This is the write path and write scaling. You'll notice there's a little bit of a crazy thing there, and we'll get to a little crazy spike in there. We'll get to that. But Bluesky has a public Firehose. So anybody can go and subscribe to a WebSocket that will spit every event that happens on the network to them. You can play back a buffer of, I think right now, 36 hours of events. You can go and see, hey, who's liking what, who's posted what, who's following whom. All of this data is publicly available. We have hundreds of subscribers to the protocol level Firehose and thousands of subscribers to a lighter weight version of the Firehose. So when our write throughput goes up, we have scaling issues both from hey, can we keep up with writes? And then also, can we keep up with broadcasting these writes to everybody who wants to consume them? So we went from a daily Firehose peak of around 150 events a second to 1,500 events a second. So this is 10x on reads and 10x on writes in less than a month. As you can see in this graph, there are some bytes and chunks taken out of this Firehose graph. Normally, what you'd like to see here is kind of like a smooth arch, and instead there's a lot of missing pieces. Particularly, this was a really rough day where our Firehose host died. So our Firehose process is something called the relay. It aggregates event streams from thousands of different servers that are in this distributed open network, and then it merges them into one gigantic event stream. And that one gigantic event stream then gets broadcast to hundreds or thousands of subscribers. So it's a lot of work for one process to do. This was running as a single Go binary on a single machine at the time. It was way more, like the hardware that was on was way more than we needed for the scale we were operating at. We would scale it up as we needed to. Unfortunately, the world had other plans, and we did not get the chance to scale it up in a smooth way. So what we ended up with were constant crashes all day long of this relay process. We were falling behind on line write traffic, which meant that there were delayed writes for the network. So you'd post something and it wouldn't show up for 8 to 10 seconds, and you'd be like, hey, what the heck is going on? Or you'd like something and you wouldn't be able to see that your like went through for 8 to 10 seconds. We propped it up just enough to minimize user impact to where people weren't like going off the site because stuff wasn't working right. But it was definitely a challenge. Here are some node exporter metrics that show what we were looking at. You can see the growing CPU utilization. You can see the growing network utilization. I think the bottom of that graph is 10 to 12 gigabit of just Firehose traffic. And then the disk space graph here, you can see we're running on these NVMe disks, and we suddenly take off. So that was not going according to plan. The relay has a compaction routine that helps it keep its disk space under control, but that compaction routine fell behind under the insane load that we were dealing with. So the whole disk filled up, and it didn't even hit 100%, and that's what killed us. What actually happened was we ran into limitations of NVMe. So there was an internal hardware failure. There was both kind of this disk capacity exhaustion, and then there was also disk latency spikes, which was causing the big problem for us, which was writes were getting delayed and we couldn't keep up with the throughput. So SSDs are over-provisioned, which means there are extra cells in them that are saved for really high write spikes, and it allows you to keep up with write spikes and keep performance through those times. But the problem is if that write spike lasts for 11 days, your over-provisioning runs out, and your SSD can't really keep up with that. So the way that SSD, if people here are familiar with NVMe at all, the way NVMe writes work is you can only write kind of a large chunk of each flash cell at a time. You can't just write like a single tiny piece of your NVMe at a time. And so the way it works is it'll mark cells that it'll take this big chunk, this big block that has some good data and some dirty data in it, and then in its free time, it will garbage collect. It will rewrite the block to a new area on the disk, and it will get rid of all the dirty data, and then you'll have a bunch of free blocks to write new data to in that section. If you are writing way too fast to your SSD and you are deleting lots of things and you're making so many dirty blocks, the SSD garbage collector can't keep up, and you end up with huge spikes in disk latency. And so what we were seeing was, usually somewhere around 300 to 500 microsecond latency under our normal load for our disk access, and then our disk access latency shot up to in the dozens of milliseconds, and that really caused the whole system to kind of grind to a halt. On top of that, we ended up with XFS file system corruption at one point. Once we were getting towards the very far end of the life of that machine, the process crashed a few too many times, and then we also saw file system corruption, which is insane. I've never actually seen XFS file system corruption before this, so that was pretty crazy. So our system load on this machine, you'll see, everything was fine until about the 16th, and then things started getting crazy, and that system load jumping from basically 0 to 4,000 is not what you want to see. That's the sign of a computer having a very bad time. So how did we deal with this? We shifted to a lower load architecture, which we were very lucky to have in our back pocket. Well, the former architecture required tons of disk space and tons of disk write per user. The new architecture that we had, which we called the non-archival relay, allowed us to throw away a lot of the storage on disk and get rid of a lot of the IOPS that were required to process this. It was in our back pocket, had been written in a PR 8 months ago and was still under review, and we were like, we might get to that at some point in the future. Suddenly we had to immediately spin that up, throw it into production, completely untested, and hope that it would solve the problem, because otherwise this node was down and the network was down. So we also offloaded subcomponents of the service. So we're serving hundreds of subscribers. We're doing 12 gigabit of Firehose traffic at this point. What if we move that to another machine and we kind of have that machine just subscribe to the big Firehose, and then all it does is kind of mirrors everything and broadcasts it out, so that at least gets the load of sending all that data off of our primary relay machine, which we need to ensure writes are coming through the network. Also, rotating in hot spare hardware. So if we had a disk that ate it or something like that, we always have a couple hot spare machines of each of the SKUs that we care about in our bare metal environment. And so thankfully, we were able to spin up one of those subcomponents on one of our hot spare machines so that we could, this was the time to throw all the levers and to put every coping mechanism into place to make sure that we stayed alive. And most importantly, divide labor among the team. At this point, we had about 5 or 6 people in the situation room at all times. And so we had 3 or 4 major tasks we needed to do to solve this problem. We solved it in about, I want to say 2 to 3 hours. And we solved it in 2 to 3 hours because we took all of these different strategies and handed them to a different member of the team and basically sent everybody to go get their part done and then got back together and shipped each of these strategies one by one. All right, one more fun Firehose thing to talk about is the Ouroboros situation. If you're familiar with an Ouroboros is a snake that's eating its own tail. We ended up in a similar situation where we created a loop in our routing that caused events emitted from the Firehose to be fed back into the Firehose, which turned into very high throughput of traffic and very large event spike. There weren't actually new events coming through there. We ended up accidentally looping for a couple of hours to our public subscribers. So there was an internal software failure. We had a misconfigured proxy deploy that was kind of shunting the traffic, the public traffic for people subscribing to the Firehose to our new internal service we just threw together an hour ago. That would offload all of the outgoing Firehose traffic for us. So we misconfigured the proxy deploy and we accidentally connected it to itself. And it ended up creating a massive buffer of repeated events that it just kept emitting to our subscribers. So this was mostly triggered by exhaustion. This was on day 10 of the 11 days of hell, and everybody was very low on sleep. There were miscommunications flying around. We weren't all on the same page. We were exhausted of being in the situation room, so we moved to DMs and Slack threads in order to have be a little bit less online in the situation room for some of these actions. And that clearly bit us a little bit. And this is also just kind of the effect of Band-Aid stacking. So when you're in a really stressful situation and you're like, oh, we can solve that, let's put a Band-Aid on it. And you go, oh, we can solve that, let's put another Band-Aid on it. And then suddenly all that's left is Band-Aids. And that's kind of the point that our infrastructure ended up in. We usually try to keep a strict infrastructure as code policy. We ended up doing a lot of manual fixes to services in production, and then those manual fixes were not checked in because we were trying to move fast and make sure that everything stayed alive, and so you get these stacking Band-Aids that lead to misconfigurations and very easy human error-caused outages. So public consumers saw a bunch of repeated events. It was about 2 hours before we noticed because we shifted all of our internal traffic to talk directly to our Firehose producer instead of talking to the public mirror, just to kind of give us a different SLA from the public consumers. It was about 3 hours from the incident start to when we resolved this problem. There were thousands of external feeds and tools that had broken as a result of this. So we repaired the broken proxy configuration. We replayed missed events for consumers because there were hundreds of consumers that had all these events. They not only saw the same events over and over and over again, but they missed about 3 hours of what was actually going on the network. So we had to replay all that traffic back for them. We have to apologize to developers and maintain good relationship with our developers and our developer community. That's probably one of the harder parts. Well, I wouldn't say it's hard, but it feels bad when you have to tell them, hey, we screwed up. I know you're doing all this stuff free and for fun and because you like our protocol, but I'm going to give you more work to do now because we messed up. That sucks. And then, from that, automate all future proxy deploys with human approval. Make sure that's automated. Make sure at least 2 people take a look at it. Make sure that goes out smoothly. I'm sure we're going to break this rule at some point in the future when something crazy happens again, but we can at least try to practice it so that it's easy to do under pressure. And then finally, self-inflicted problems get more frequent when the team is exhausted. When the team is tired, if you can't rest, double, triple check everything. For us, we're such a small team that every hand was needed for the entire basically 16 hours a day to handle peak and anything we wanted to ship at night to solve tomorrow's peak. We were all dragging, we were all getting pretty tired, and that leads to a higher frequency of issues. So let's talk about an incident that was a little bit more positive, which is a celebrity caching problem. So if you have been a Twitter user in the past, you might have heard of this as the Justin Bieber problem or something like that, which is there's a very small number of users who get the vast majority of the traffic that comes through your network. People are trying to go look at Justin Bieber's posts. People are trying to load or go like Justin Bieber's post. People are trying to load a thread that Justin Bieber started or whatever it might be, and that gets pretty complicated. So for us, we have a horizontally scalable sharded database, which usually works great as long as traffic is evenly distributed. But when it's not evenly distributed among shards, we get really bad P99s. And so we had P99 database queries spiking to 100 milliseconds when they're normally 2 to 4 milliseconds. And this was an internal software failure. Our sharded database meant that each data partition is only served by 3 cores. So even if you have 2,000 cores in your cluster, only 3 of them can be used to serve one specific piece of data. And so if that one specific piece of data is Justin Bieber's profile, and everybody's trying to load Justin Bieber's profile, then you've only got 3 cores doing that work. They get overwhelmed. Those celebrity accounts, those popular accounts, have hot data on the read path, and DB-tail latencies for everything spike when a core gets hot because data is randomly distributed, and that those shards own more than just the celebrity's data. They also own thousands of other partitions of random users. And so when you go and you make a query, we have a fan out in the hundreds. So every API request that you're getting is turning into hundreds of database queries under the hood. So P99s get hit multiple times for every database query. So all API requests were feeling the pain of these hot shards. So how did we solve it? Well, in the brief window of time between daily peaks, we managed to get a cache going for popular actor data. This is a dynamically configured hot set. So basically, each data process has an in-memory cache. They talk to Redis, and Redis gives them a set. Every 30 seconds, they refresh the set from Redis, and they say, hey, who are the popular actors? Who are the popular actors? And then that basically decides the caching policy that node will use. So sync the config, not the data. So you have these big data processes. You want to sync. You don't want to sync the caches between those nodes because that's a lot of data to move, and you're going to crush Redis to death if you try to move all of that data through Redis at the throughput that we deal with. So instead, you sync the cache configuration, and then each of your data processes themselves can manage their own internal caches. They'll get hot quick enough. It's not a huge problem. Give the database a break. Cool. So after we deployed this caching strategy, you can see that the database query P99s the following day were down to 10 milliseconds instead of 100 milliseconds. So it was a 90% reduction in query P99s. Additionally, there's 50% lower peak query throughput because literally half of our database queries for profiles were for the list of celebrities that we ended up putting together to solve this problem. So I guess kind of a lesson here is the shape of your data and the shape of your querying, heavily impacts what strategies are going to be really impactful. I had no idea at the time that I was writing this caching strategy that celebrities were making up a full 50% of the query throughput. I had a guess it was a high number, and then when shipping this, seeing that throughput drop basically in half was incredible. That was very validating. It was like, yes, this was the right decision. Cool. I have time for a few quick more short stories from this week. Remember, this all happens in an 11-day period. This was kind of insane. So, invalid handles. If you've used Bluesky, you know that your handle, which people use to @mention you, is actually a domain name. So you can bring your own domain name, or you can use one that we provide for you. Those domain names are really cool because they're validated using public DNS infrastructure or they're validated over HTTPS. That's really cool. It does require doing a lot of DNS lookups to make sure that handles are valid. So it turns out public DNS has limits. I learned this for the first time during this incident. So if you're talking to Google's public DNS or you're talking to Cloudflare's public DNS resolver, they're probably going to rate limit you at around 5,000 queries a second. Keep that in mind. That's a good number to know. We learned that the hard way. So it's about 5,000 queries per second for both, I think, 1.1.1.1 and 8.8.8.8. So if you use public DNS, don't try to query it more than 5,000 times a second. They will ban you for 5 minutes and then let you back, and then ban you for 5 minutes and let you back for 5 minutes. And this causes a bunch of people's handles to go invalid on Bluesky. So during a massive influx of new users, millions of new users had invalid handles. This was really, really bad. It made it hard to search for people. It made it hard to mention people. It made the site, somehow people kept using the site despite this, which was awesome. But this was a pretty bad optics on this incident. So how do you deal with that? You run a local DNS resolver and you talk to your public DNS providers and you ask them for limit bumps and say, hey, we're a big internet company. Well, we're a small internet company doing big internet things. Can we get our limits raised? And then eventually they might say yes and give you limit raises. But running a local DNS resolver in your data center that you can point everything at, or a couple of them that you can point everything at, allows it to do internal caching, allows it to do all sorts of stuff that makes this less of a problem for you. One fun quirk in here is that the DNS resolver that we use, the way that DNS handles work is you can either verify via DNS or via HTTPS. And so if you're using a well-known HTTPS verification for your handle, you can't reuse TCP connections because every handle is a different subdomain, and your HTTP client will not allow you to reuse a TCP connection that's to a different domain name. So there were lots of cool strategies that you usually use to solve making tons of requests to the same hosts. But in this case, we couldn't use a lot of those strategies. So this got, this was a hard problem to solve on top of all of the other stuff that we were dealing with. It was a lower priority problem because it wasn't the service is unavailable. It was users are confused and this is kind of bad, but this made it a less of a critical issue. But we still fought through it and got rid of it. What else did we do during this time? These are just some short little graphs here. This is the network throughput coming to, I believe this is data received by one of our infrastructure nodes. And this was when we decided to drop sending OTel traffic to our infrastructure node because it was consuming so much of our internal network bandwidth, and it was also eating lots of CPU on that host, which was running a couple other services on it as well. So things that you can do is drop some ballast when you're under load. In this case, you don't really need perfect fidelity tracing of the insane 10x event that you're going through. What else did we do? Oh, so this is our search service. Our search service, the green there is the searches, like somebody typing in a username and hitting enter. And then the orange there is searches for a type ahead search for an actor. So if you are actively typing into the search bar, you'll send a couple of those orange queries. Or if you're mentioning somebody, you'll send a couple of those orange queries. When you hit enter is when the green query goes through. But you'll notice there's a ton more green queries than orange queries, which is a weird shape. It turns out there was a Chrome extension that people were using that was scraping your Twitter follows and then hitting our APIs to try and search for those users on Bluesky so that you could migrate. And this presented itself as a massive DDoS to us because there were thousands of different web browsers that were all running this Chrome extension from different IP addresses that were literally just slamming our search APIs nonstop, trying to find people that they were going to follow. We managed to get in touch with the developer of this Chrome extension and get them to ship a patch. That was very scary because I was afraid, this was going to cause some serious problems forever because people just leave Chrome extensions on and it was doing it in the background. And it's just, this is our life now, is we're just going to get tons of garbage search queries coming through all the time. Thankfully, we saw an inversion of this trend where the type-ahead search, which should be getting called a lot more frequently, ended up becoming the dominant query throughput at the end there. But we were doing, just in one data center, almost 2,500 searches a second. So across both data centers, it was closer to 5,000 searches a second for actors. And then after that, things definitely calmed down to a more reasonable rate. And then one more thing I've got is Discover, which is the kind of the main algorithmic feed that we have, had some very significant growing pains. Its P99 latencies, went to the moon. This sucked. The Discover at the time was deployed onto one machine. It had its Postgres instance running next to it, and then it had its Go binary running next to that. What happens when you start caching lots of data in your Go service is you start eating into the page cache that's available for Postgres. And so when both processes on the machine want to make use of the memory, and Postgres' usage of memory is passive in that it doesn't claim the memory, and your Go service's usage is active, which means it does claim the memory, the Go service will just eat lots of RAM that Postgres was depending on, and then Postgres will start to perform worse and worse and worse until your latencies get really bad. So this is another big reason to isolate your workloads and split them when you can. We were running on a pretty small hardware footprint at the time, and so we were trying to consolidate as much as we could. And so this was motivation to say, okay, we probably need to allocate a machine specifically just for the database for this one service. Cool. How did I recover? I went to the data center and I racked a bunch of new servers. I ran a lot more fiber. So we made it through on the original hardware that we had. So that was a blessing. But we were like, all right, how are we going to be ready for the next event? Run more fiber, rack more metal. Some tequila was involved. Got a nice bottle from a coworker for keeping things online. So that was appreciated. And then, spending some quality time with like pets and friends and family or whoever you have to spend quality time with. So I got to go see the family dog and pet a dog to kind of calm down. There's still a lot of trauma there from those 11 days and from like bearing the weight of the website must not go down on your shoulders nonstop for 11 days. It's a lot. I feel like it aged me like 5 years in a very short period of time. But I feel like I came out the other side of it with a bit more resilience to those kinds of situations and with a bit more of things will go down and that is nature and we will roll with the punches and figure out how to make things come back up and we'll deal with it rather than something going down is the end of the world. So that's my talk. We are hiring an SRE role right now. So if you are interested in these kinds of problems and you happen to be plugged into @Proto or interested in building distributed social, there's a QR code and there's a link there. I think we have a Go role open as well right now, as well as this SRE role that's probably the most relevant to people that are here. And that being said, do we have any questions?